In this video, we will learn about Le Chatelier's principle, which is about changing conditions and how the system will respond to those changing conditions. So this is a phenomenon named after a scientist named Le Chatelier. Scientists like to study systems, and one way that they can study systems is by messing with it. Like if we notice that the system's at equilibrium, then someone's going to come along and try to figure out what can speed up the forward reaction, what will slow down the backwards reaction, which way can I shift my reaction so that I can get it to do what I want. And so Le Chatelier is a scientist who's going to be messing with the system to see how it responds. So once you reach an equilibrium, we know that the relative concentrations of reactants and products stays constant. There's no change to the concentration of reactants and products because the rate of the forwards and reverse reactions is equal. But we can just dump in a whole bunch of reactants, and that's going to change the rate of either the forward or backwards reaction, depending on what we're doing. Are we adding more reactant? Are we adding more of the products? Are we changing the temperature? And so our goal is to predict which direction a reaction will shift when our equilibrium is disturbed. So here's our analogy. At equilibrium, the rates of the forwards and reverse reactions are the same. And so we draw our reaction arrows the same size to indicate that they are equal and opposites, so that they're not changing anything. This is like running on a treadmill. You're running forwards, but the treadmill is running backwards. And so you're constantly moving, but you're not getting anywhere. So you're at equilibrium on this treadmill, but you just adopted a new cat. And cats are known to be assholes. And so this cat is going to disturb your equilibrium. Now, there's a couple options here. The first option is that your cat turns off the treadmill. And we need to figure out which way you're going to fly. Go ahead and try to figure out which direction you would fly if the treadmill turns off. Well, let's draw our arrows again. So here's my forwards reaction. I'm running this way, but the treadmill turns off. And so I have killed my backwards reaction. So I drew a very small arrow, but if the treadmill turned all the way off, it would be no arrow at all. And so what happens is that you fall this direction because that's the direction you were running. And so we call this shifting right. You can tell that our arrow points towards the right direction. So this arrow here points in the direction that we're shifting. So our reaction, the forwards reaction, is going to be going much faster than the backwards reaction. So more products will form. Another option is that the cat turns up the speed. Now, if the cat turns up the speed, then here is how fast we've been running on that treadmill. But now the cat turns up the speed of the backwards reaction. And so what direction do we go? We shift left. And so this means that we are going to be reforming more, the backwards reactions going faster, and so we will be forming more reactants and using up more of the products. So Le Chatelier's principle, he came up with this principle like a really long time ago before they really understood molecules and atoms and stuff, but his principle says when a chemical system at equilibrium is disturbed, the system shifts in a direction that will minimize the disturbance. And so this explanation of Le Chatelier's principle is like the classic explanation, because they didn't really understand molecules or atoms or anything like that. And so it's kind of putting a personality on the reaction and trying to say that it's going to undo whatever you did to it. But we're going to be trying to explain, I'm going to be trying to explain it in terms of reaction rates so that you can kind of more conceptually understand what is happening. So let's think about our frequency of collisions and what reaction rate is going to speed up. So initially we're at equilibrium where we have A turning into BC. This is like a decomposition reaction. And then in the reverse reaction, we have more of a combination reaction where B and C combine to make A. So now let's say that we add a whole bunch of A. If we add a whole bunch of A, that takes my initial forwards reaction and makes it where that is much, much bigger than my backwards reaction. The backwards reaction is still going, but just not nearly as fast. So the backwards reaction was going like that. And then this is going to make the forwards reaction so much faster because we have a whole lot more A molecules that can go this direction. So we're going to be shifting right. But eventually, we are going to make so much B and C that, and use up A, that eventually we're going to reach equilibrium. But now let's look at our contents of the box. Compare the contents of this box at equilibrium to our initial box at equilibrium. You might notice that we have a whole lot more A in this reaction than we did before. And so we still have the same equilibrium constant, but we can have different molarities of B, C, and A that all equal that same equilibrium constant. And so overall, we have more A molecules, but we have reestablished equilibrium. And you can see that we actually have 3 molecules of C and 3 molecules of B. And that has allowed us to reestablish equilibrium by increasing the amount of B and C because we have shifted right. And that counteracts how much A we added. So let's look in this in terms of like another chemical reaction, something that has actual chemical formulas to it. And so as we add reactants, it will cause this to shift towards the right, towards the products, because we would be speeding up that forwards reaction. So if we add more NH2 and add more NH3, then we are going to be causing more collisions to happen between those molecules. which will increase the rate of reaction for the forwards reaction. So adding reactants will shift the reaction this way towards the products. Similarly, we could achieve the same effect by removing NH3. So if we remove a product, so if we're at equilibrium, then if we add reactant, then that's going to speed up the forward reaction and kill the backwards reactions the same initially. And then if we remove product, what that does is our forwards reaction was the same as it was initially, but now our backwards reaction has essentially slowed down. So it has the same effect, but for different reasons. And so both of these shift right. So if we look at this graph, initially we were at equilibrium. You notice that all these lines are not changing their concentration. The concentrations are constant. They're steady, not changing, so they're at equilibrium. And then we add a whole bunch more N2, which is a reactant. Now, some of that N2 is going to get used up, and some of that hydrogen is also going to get used up at the same time. And then we reform products. And so here they've used numbers to show that once equilibrium is reestablished, we do have more product. And that allows us to have the same equilibrium constant that we did before. If we wanted to shift left, we would do the exact opposite. We would add product and remove reactants, and then that would shift us left. An important note is that only concentrations of substances that appear in the equilibrium expression matter. That means that if I do something like adding helium or argon or something that doesn't matter to this reaction, it's not going to do anything. All right, now let's talk about how changing pressure or volume would affect things. So this is mostly for gases. Gases is what we have to worry about pressure and volume for. But it says an increase in pressure will shift the reaction in whichever direction produces fewer moles of gas. So we have to think about how this statement is applied. So it says if we increase the pressure, more collisions are between there's more collisions between gas molecules. So that's true. And then we will increase the rate of reaction between our gas molecules because now they're under high pressure. So if we look at this example problem, we have 1 mole of gas on this side. And then here we have 2 moles of gas. And so if we increase the pressure, then we're going to have this backwards reaction happening more often because these molecules are going to find each other more than they did when the pressure was lower. And so if we increase the pressure for this example, then my backwards reaction is going to go more, and the forwards reaction is going to stay the same. And so fewer moles of gas So increasing the pressure shifts in the direction where you have fewer moles of gas. So it's not always like a left or right. You really have to actually look at how many moles of gas there are on both sides. Another thing to remember is that increasing the pressure also decreases the volume. So if we increase pressure, it will have this effect. But also if we decrease volume, it would have the same effect. So here you can tell in the picture that once we've increased the pressure, we do have more N2O4 than we did initially. All right, next up we have changing temperature. And so we have to think of heat in terms of like heat as a reactant or heat as a product. Adding heat will make the endothermic direction more favorable because endothermic reactions absorb heat. And so we add heat, that's the direction that it's going to want to run. So we have to think in terms of, hey, if my reaction is exothermic one way, in this one, this is positive. And so this particular reaction is endothermic this direction. And that means the backwards reaction, delta H reaction equals positive value. That means for the backwards reaction, my backwards reaction must be exothermic. So if we look at this is positive, so if this is positive, that direction is endothermic. And for endothermic, heat is a reactant. And then if it was exothermic, heat would be a product. Okay, so now that we have heat as part of our equation, we can think of it in terms of adding or removing of reactant. So if I add, so here, I'm just going to rewrite it. So we have N2O4 plus heat, 2NO2. If I increase the temperature, then that means I'm adding heat. It means I'm adding more reactant. And so if I'm adding more reactant, that's going to shift my equilibrium, speeding up my forwards reaction and keeping my backwards reaction about the same. So I'm going to shift right in this case because I'm endothermic. All right, here's a practice problem for you. How about you go ahead and pause the video and try to figure out what each of the following options would do to the equilibrium. Try to decide whether the reaction will shift to the left or shift to the right, or if there will be no shift at all. Okay, let's go over this. First up, if we are condensing and removing at SO3, condensing means changing from a gas to a liquid, and then we're removing it. So we're basically saying we're removing a product. So we're removing a product. Removing a product is going to kill that backwards reaction. And so the forwards reaction is going to go faster than the backwards reaction. So that's going to be a shift towards the right. Okay. Next up is compressing the container. And so this is going to increase the pressure. We're going to increase the pressure. So we got to figure out how many moles of gas we have on both sides of the equation. Here I have 3 moles of gas. And here I have 2 moles of gas. And so if I increase the pressure, this side has more gas, and so it's going to bump into each other more often than it did before. And so that's going to shift my reaction towards the right. So that's going to make my forwards reaction faster than my backwards reaction. All right. Now we have cooling the container. So for cooling the container, we really should look at this delta H value. This delta H value is negative, which means it's exothermic. And so that means my heat is a product. So if I'm cooling the container, that's like removing a product. So cooling the container is like removing a product. That's going to shift my reaction towards the right, because my backwards reaction is going to slow down considerably. Next up, we have doubling the volume of the container. So doubling the volume of the container is going to make my pressure drop. And so that's going to have the opposite effect than increasing the pressure did. So that's going to shift my reaction towards the left. Okay. Now we're going to warm the mixture. Warming the mixture will do the opposite that cooling the mixture did. And so cooling the mixture shifted us right. Warming the mixture is going to shift us left. Now we're going to add helium to the container. Helium is not in here at all. So helium is not going to matter. Now you might think that adding a gas would shift the equilibrium because of more moles of gas, but we're really thinking about the partial pressures of each gases. And that's not going to change the partial pressures of each gas that we actually care about. All right, now we're talking about adding more O2 to the container. So this is adding a reactant. So we're going to add more reactant here. That's going to shift us towards the right by making our forwards reaction much faster than the backwards reaction.